Revitalizing Science and Values. The deadline for the call of paper is November 15th. And you can find some more information on the center's website. Today, it's my great pleasure to introduce David Waszek, who is obtained his PhD in Paris from the University Paris 1, Panthéon-Sorbonne. Right now, he's based at the École Normale Supérieure, the best place in the world. So I got my kid. Who has spent years as an undergraduate. So wonderful place to be. David works on mathematical representation and more broadly on how mathematics is represented. He has done some work connecting mathematical representation and computation as well. He's currently a fellow at the center, so we have been really happy to have him here for the whole semester. He has various connections to Pittsburgh. One of them, he has done work on Ken Mendes, and actually he's reading with Ken Mendes' house. It is not too personal to say that. So he has actually a connection. He has also published on Herb Simon. So actually there's an intellectual connection with the city of Pittsburgh. So we're really happy to have you here this semester. David, floor is yours.
Thank you very much for your introduction. Thank you all for coming to listen to me today. Here's a very visual outline of my talk. I am a historian, or at least I do a lot of history. So I'm a bit like this ant, and I do this very tiny stuff. And we're going to get to that eventually. But I wanted to start by a bigger picture to try and place what I do in a broader context. Of course, ants are not necessarily the best at describing, planet Earth or, the broader landscape. So I hope I won't mess that up too much. Okay, so what I'm going to start with is some elements of motivation, detour through the applications of mathematics, and then some general considerations about language notations and accessibility, especially with respect to mathematics. And then I'm going to move on to the ant or the leaf, depending how you interpret it, and present a case study. So you can see the first two sections as a kind of extended introduction and less original material, maybe. Okay, so the application. So I want to start with the problem of the applicability of mathematics. So it's a notoriously slippery kind of problem to get one's hands on. It's not always clear what the problem exactly is, what would count as a solution. Here's a typical formulation from a well-known recent book by Bueno and French. How can something apparently so different from science be so useful in scientific practice? And so there's something so different from science is mathematics. So here there are two elements. There's the difference, heterogeneity, and there's the usefulness. Discussions, however, for various reasons, mostly to do with ontology, often foreground the heterogeneity aspect of the problem. We have abstract mathematicals on one side and the empirical world on the other. How can the former apply to the mathematical? And the typical idea that one starts from is, well, it's some kind of structure preserving mappings that bridge the gap. So maybe mathematics studies some kind of abstract structures, or maybe objects that stand in abstract structures, and then you can connect them with some aspects of the structure of the world, and so you solve the problem that way. This raises various issues, which motivates more recent accounts. I'm going over terrain that I think should be familiar to many of you here. So you have problems with idealizations, which lead to the question, can the structure and the empirical sides that you're trying to connect really be described independently of the mathematics? And then you have what Bueno and French call a problem of surplus structure, a term they borrow, I think, from Michael Redhead. The mathematics often appears richer than the corresponding empirical structure. A typical example given in this connection is complex numbers. So maybe you're describing something to do with real magnitudes, but you're going to use complex numbers in your math. Sometimes parts of this surplus can eventually be ascribed an empirical interpretation, but not always. And so you have this kind of, it's not clear what exactly the mapping should connect, how it works, and so on. This is the kinds of considerations that motivates this popular conception presented in Bueno and Taliban and also in Bueno in French, where you have a setup like this. So actually you have not one structure preserving mapping, but two, which are the arrows in blue, okay? And then you have something happening truly on the mathematical side. So you start from an empirical problem situation, whatever, you immerse it into a mathematical structure. This can be partial immersion, so you can have more mathematical structure than you have empirical structure. You can do some math, and then again, you can have a mapping to bring you back to the initial problem. And this can allow you, the two mappings need not be the same. The two mappings allow you to bridge the problem that we had earlier between the mathematics and the world, but in a flexible way. That allows you to answer the queries about substructure or idealizations. At least that's the idea. I'm not going to get into whether we think that works or not. The point I want to make is simpler and I think quite straightforward. So let's first see what Bueno and Colivan writes about this account. The fundamental role of applied mathematics is inferential. By embedding certain features of the empirical world into a mathematical structure, it is possible to obtain inferences that would otherwise be extremely hard, if not impossible, to obtain. And so the advantage of the math is that what's happening here in the derivation step, the math can allow you to get inferences effectively, can make things accessible to you that otherwise wouldn't be, but you don't need necessarily to then map them, map the elements that help you do this onto the empirical world. That's the story. This story, again, is motivated by heterogeneity concerns. One thing that it does not answer to is the other parts of the question that we started from, namely the usefulness bit, at least not in a straightforward way. In itself, this does not help at all with the usefulness question. Why would the mathematics offer us useful inferences in the derivation step in the first place, at least in some cases? In this way of framing it, the inferences come like a rabbit out of the hat. It's not clear what allows it. You just take it for granted, and then your worry is, does it have corresponding things in the world? Now, to make this problem maybe even clearer, you can compare using the move, since Edouard wrote up Kahn-Mandus, that Kahn-Mandus emphasized in a draft long ago called Why Apply Math. You can compare the situation to applications of mathematics to mathematics. Here's a very Mandusian example for a bit. You could start from a geometrical problem. You could convert it into an algebraic equation, do some algebra, get some solutions, maybe several, maybe some of them will be interpretable, maybe some not, you can have negatives, you can have imaginaries. And then you try to see what this can tell you about the original problem yourself. This kind of mathematical strategy, very common, is easy to fit into Bueno and Colivan's mold. So I've just used the same diagram here. There's no problem with presenting it in this way, but I think once you see it in this kind of example, the point I was making on the previous slide should be abundantly clear. Decomposing the strategy into these arrows brings us no closer in itself to understanding why the detour through algebra can, in some cases, prove useful. It's not the same question. Okay, so one worry could be there is nothing to be said here, or maybe this is just, it just happens to work and we don't want to say more. I think there is more to be said. So this is kind of way of framing the problem. So to rephrase this, why can it be useful to apply mathematics? Basically, Bueno and Colivan respond because mathematics alters which inferences are epistemically accessible to practitioners. But why and how is mathematics able to do this, to alter what is epistemically accessible? And here, in this kind of framework, we have no answers. This is not what it's built to provide. Okay, so from this setup, where do I want to go? As I said, giving you the example of the algebra and geometry, the problem arises inside mathematics just as much as in applications. And my focus in the case study later on is on pure mathematics. Further, the angle I should adopt is to restrict my focus to the way mathematical language can impact epistemic accessibility. We could discuss how deep that goes, but it's a very important aspect of it, at least. Okay, so that's something. Now, let's step back a little bit. In very general terms, before going into case study, in very general terms, the simple idea, that the language one uses orients one's inquiry and shapes what is practically accessible should be a familiar one. In other contexts, it is often mentioned. Here I've just given kind of two classical passages that elaborate on this theme of a maybe broadly speaking pragmatist vein. Well-known passages of the philosophical investigations here. Language is an instrument, writes Wittgenstein. Its concepts are instruments. Now, perhaps one thinks that it can make no great difference which concepts we employ, as after all, it is possible to do physics in feet and inches, as well as in meters and centimeters. The difference is merely one of convenience. So one might think, says Wittgenstein. But even this is not true if, for instance, calculations in some system of measurement demand more time and trouble than we can afford. So there are constraints here of a practical, pragmatic nature. Pithic formulation concepts lead us to make investigations. They are the expression of our interest and direct our interest. Maybe vague, but familiar. And another one in the spirit from a much more recent literature, but expresses the sentiments in ways that should be familiar, from Evelyn Fox-Keller and her Century of the Gene, a well-known final part, elaborating on the role, gene talk plays for scientists, even if maybe it does not have unified underpinnings always, and so on. The words scientists use play a crucial role in motivating them to act, in directing their attention, in framing their questions, and in guiding their experimental efforts. All right. So in broad terms, this shouldn't be too surprising. Now, in mathematics itself, the idea of thinking of symbolic calculi in terms of accessibility used to be a significant theme in methodological reflections. It's a bit less so nowadays for various reasons linked to the development of the discipline. Used to be prominent. I'm giving you, again, one very well-known passage elaborated on in a paper by Audrey Yap from her first career as a philosopher of mathematics. This is a well-known quotation by Gauss, commenting on the role of calculi, such as algebra in general, the differential calculus, his own calculus of congruences, and others. This is a letter from fairly late in his life, laying out broader methodological principles, you could say. In general, the situation regarding all such new calculi is this. One cannot accomplish by them anything that could not be accomplished without them. So it's not that it would be impossible otherwise, it's more a question of accessibility. Their advantage, however, is that if such a calculus corresponds to the innermost nature of frequent needs, anyone who masters it thoroughly is able to solve the relevant problems. So the problems that, this calculus makes more accessible, so to speak, mechanically, even in cases that are so intricate that genius itself becomes powerless without such an aid. Bit flowery language, but the idea here should be clear. And I invite you to have a look at Audrey Yap's paper. Instead, I want to spend a bit more time on Boole, another figure who has been very explicit about such kinds of methodological considerations, and who in the first chapter of his investigation of the laws of thought makes the link between calculi and accessibility very explicit. Maybe I should say a few words about this absurd picture here on the right-hand side. I was asked to review a recent book by a foremost expert on Boole a few years ago. And in one of the later chapters, the author elaborates a weird theory that Boole was the model for Professor Moriarty, the evil genius of Sherlock Holmes stories. There are lots of disturbing coincidences, like they were both tall and mathematical geniuses, and Boole knew someone who knew someone who knew Conan Doyle, and that kind of thing. And so the authors ran with it and made this composite picture of Boole superimposed on the image of Moriarty that you find up. Okay, never mind. All right, so what does Boole say about calculi and accessibility? For Boole, the whole point of a good calculus is to help guide us to the solution of problems. The paradigms for him are the symbolic calculi of algebra and analysis. His logical calculus is meant to accomplish something similar for logical problems. This guidance function requires doing more than just listing what the fundamental operations are that one may perform using the calculus. So it's not just, as one might think of a calculus today, well, you have the rules for how you can commute terms of an addition or a multiplication. You can put a term on the other side by subtracting both sides. You have these rules. It's not just laying out the rules of the game. It's telling you how you can use it and designing the calculus so that it affords you ways of using them to get to the solution of a problem. So I've given you a couple quotes. I committed with Dirk Schlim a paper on this where this is gone into in much more detail, comparing it with Frege and so on. So in case this is a bit obscure, have a look at that. Here's what Boole says. If all inference were reducible to syllogism and conversion, so he's going to set up a new logical calculus. The fundamental operations are different from syllogism and conversion. It's about combining classes and so on. But he says, even if it were true that you could reduce all logic to syllogism and conversion, the traditional logic would nevertheless still be defective. Why is that? Because it does not afford you a general method. It would still be requisite to determine in what order the processes should succeed each other, as well as their particular nature, in order that the desired relation should be obtained. So this is not formulated in the clearest way, but so basically which steps you should use and in which order if you want to get to a certain reasoning conclusion. So he has an idea of what a logical problem is that we could talk about that. I'm going to skip here, but so he has an idea of what the goal of reasoning is. And then, you should have a method to tell you what kinds of steps you should use and not just know what the elementary steps are that your calculus supports. The comparison with mathematics is very clear here. If we may judge from the mathematical sciences, which are the most perfect examples of method known, this directive function of method constitutes its chief office and distinction. The fundamental processes of arithmetic, for instance, are in themselves but the elements of a possible science. This is what I said. If you have the elementary rules, that's not enough. To assign their nature is the first business of its method, so it's good to know what the fundamental processes are. But to arrange the succession, how you put them together, is its subsequent and higher function. And here is a crucial sentence. In the more complex example of logical deduction, the aid of a directive method, such as a calculus alone can supply, is indispensable. So here, he establishes a link that's maybe not so obvious. He says, when you have complicated cases, you need a method that tells you where to go, that directs you in your problem solving. And this, he says, only a calculus can supply. So something that's designed to afford you access to the right move, or that makes them easily salient for you in the right way. At least that would be one way to gloss on this. All right. So this all being said about the importance of accessibility considerations in shaping the languages of mathematics, where should we start to explore this further? So I've given you famous quotes, broad methodological reflections. These seem to be about systematic accessibility changes in problem solving that are allowed by a full-fledged symbolic calculus. From the point of view maybe of history of science, they tend to have a bit of a textbook quality about them. So you have this calculus and you say, well, look, we have this nifty tool. It's called the congruence calculus. You can do all these things with it and see how it's nice to guide your attention. It's a bit maybe textbook-like. It does make them particularly suggestive, but also tricky to study. And also the fact that they are broad, changing accessibility for a whole range of problems make them maybe a bit hard, difficult, not so tractable, I'd say. So the case study that I want to present instead is about the smallest, basically, possible notational change I could find, and is fully situated within the context of inquiry, where you're going to have to, what do you choose, what do you do next, and so on. Other than that, however, it is a very well-known case maybe was a well-known case in mathematical circles at the beginning of the 19th century as kind of an exemplar of good method or as interesting method. What is it? It's this thing. A very small change in the Leibnizian differential calculus. So the case study focuses on the following notational change, which Leibniz introduces in two steps, around 1694, 1695. So first, instead of having just differentials that you can repeat, I go back a little bit to what those are later on in case you haven't seen the calculus in its historical form, let's say. Instead of writing d dx, you will write d to the exponent with an exponent 2x, d square of x, d3 of x with d dx, and so on, and you can abbreviate all of them. And then later on, d0 of x is x, d to the power minus 1 of x is the integral of x, d to the power minus 2 of x is the integral of x, or as Leibniz put it, the sum of x. This part, has not been preserved mostly, or at least not in the most usual setups. Since I have this nice picture of the draft where you really see Leibniz introducing this, and I go back to why I wanted to show it to you. Actually, when I started working on this case during my PhD, I did not have this. Probably it hadn't been digitized yet, and if it had, I had no idea how to access it because it was lost in a pile of manuscripts that had nothing to do with it. But it's kind of a smoking gun for the hypotheses I was making, so I'm very happy that it appeared eventually. Okay, so why was this notation famous? Over a few months, the notation appears to lead to startling discoveries by Leibniz and Bernoulli, including Leibniz's analogy between differences in powers. So what is it? So if you have a square of or power of a sum like x plus y to the power 2, you probably remember you can write it as x squared plus 2xy plus y squared. Okay. Now, if you differentiate a product, nowadays we would say you derive two functions, or maybe you say differentiate in English actually. Two functions, the product of two functions, then two times, then you also get a similar formula, d dx times y plus 2 dx dy plus x d dy. This falls out of a rule that if you differentiate the product of two functions, d of xy, you get x dy plus y dx, something like that. Okay, and here you have an analogy. Actually, formally, this is very similar, and here I've highlighted the corresponding exponents. If you use a notation where y is actually d to the power 0 of y, dx is d to the power 1 of x, and so on. So if you use the notation we saw earlier, the two cases become parallel. All right. So this is one thing that the notation at least purportedly led to. That's a case we'll have to investigate. It also led to a peculiar calculus developed by Johann Bernoulli that allowed him to compute integrals successfully by treating the letter d as though it were an algebraic quantity. And there are further later ramifications of this. But here I want to focus really on 1694, 1695, and how, in the context of inquiry. What are the goals of the case study? First, I want to show that the notation used did play a guiding role. So that's not obvious, even though, people have claimed this a lot, but often it was kind of a just so story. And in order to avoid that kind of just so stories, you want to carefully distinguish in the context of inquiry the various motivations that the researchers may have had for introducing the notation from what it later did. You want to be careful about how it looked in the context of inquiry itself. Moreover, I want to highlight the complex methodological considerations that factor into practitioners' decisions, again, in the context of an inquiry with limited knowledge, and especially, decisions like how do you write the thing, what kind of notations you adopt. You need to make that kind of decisions, even if, you don't know, you don't have the hindsight. But, and I want to highlight the role of values. So maybe you would call them epistemic values, but nevertheless, clearly values that distinguish the various practitioners in this episode in that kind of connection. All right. So maybe some mathematical background. I don't know how much I should give. So I wrote a couple of slides here. Going back maybe to the exponential notation itself. That's something that was well established in the context of this particular inquiry. Descartes, wrote, I write AA or A to the power 2 to multiply A by itself, and A3 to multiply it once again by A, and so on to infinity. So you have these shorthands, or at least they look like shorthands. And then you have a further step that was also well established when Leibniz was writing, that you can generalize this notation also to fractional or negative exponents. This is something that Leibniz learned from Newton, from a letter that became famous in their later controversy. In the same way as analysts, instead of A, and so on, are used to writing A squared, A to the power 3, and so on. So I, instead of the square root of A, the square root of A3, the cubic root of A5, and so on, I write A to the power 1 over 2, A to the power 3 over 2, A to the power 5 over 3, and so on. And instead of inverses, 1 over A, 1 over A squared, 1 over A third, I write A to the power minus 1, A to the power minus 2, A to the power minus. So that was kind of a big unificatory move that Newton made, the point of which was that it allowed him to give a general formula for the power of a sum. So if you have A plus B and you raise it to a certain power Z, with that possibly fractional or negative, so even if you have these kinds of new conventions, you can get a formula for this, which looks just like the formula for A plus B to the power 2, but in a more complicated way here. Out of historical scruple, I wrote down a historically accurate rendition of how Leibniz would have written it, but basically it's an infinite series version, or potentially infinite series version of the kind of formula we just saw for A plus B squared. So you have A squared and then 2AB and so on. That's the case where you have 2, but then you have any other exponents. Okay. Second background, I want to be quick here. The general framework in which these authors are working is Cartesian geometry. So it's based on curves and variable quantities. This means that there are no functions. So that's why maybe the notation is immediately noticeably different from what we might have. Just have X, Y, Z, and so on. And then you just differentiate variables. And variables are basically quantities that vary along the curve. They are not functions of another quantity. They're just things that vary when you move along the curve. And then for any variable quantity associated to a curve, you can form its differential, dx, and its sum. So basically an infinitely small differences if you have, imagine infinitely close points on the curve, and so on. Also the sums, and you can iterate ddx, ddx, sum of the sum of x, and so on. And actually, this is important in this connection, the differentiation and the summation are reciprocal, something that we still have today, but in a different conceptual setup. What's good about this is that you have rules that allow you to differentiate a complex variable. I mean, complex in the sense of a variable that's built out of other variables, like x plus y, in terms of the differentials of the variables. So you can have d of x plus y is dx plus dy, just as today would say the derivative of f plus g is the derivative of f plus the derivative of g, and so on. And the same for a product. And this allows you to transform any algebraic equation into a differential equation, from which you can find tangents and so on. Now, the main research problem that's they are working on and they are worried about due to considerations in physics, but also more geometrical considerations, is the inverse problem. So you have a differential equation and you want to try and determine the curve, and that's kind of part of the background of why they're doing what they're doing. In the episode later on. And here, maybe depending on the time, will be quick. Of course, we're talking about a notational choice to write higher order differences just like powers. Maybe this was based in the fact that Leibniz already knew that they were parallel in an important sense. So was it the case? Is this, is this like you find a good name for something that's, you've already understood the connection, or does the notation play a more substantial role here? And so one thing to be said is that Leibniz had this idea that there was an analogy between the two cases. But it's not actually, from our point of view, it's not the right one. It doesn't align with what he does later on. So he has this pre-existing idea that there is an analogy between powers and roots on the one hand, and differences in sums on the other hand. What is the analogy? Well, both are pairs of inverse operations. So you take a square and then you take the square roots, you go back to where you started from, you take the differential, and then you take the integral, and then you go back to where you started from. So that's kind of, it looks similar. And then you have kind of deeper similarities, apparently. So if you have an equation of the form y to the power n is equal to some complicated expression without y, well, you can extract the root. You can say y is equal to the square root, for instance, or the nth root, and so on. Even though in some cases, this, it's not clear what the symbol means exactly, because it might be irrational. So you might only have a way to express this as approximations. You might not be able to express this as a fraction. On the other hand, if you have a more complicated algebraic equation, yn is equal to yn minus 1 plus 2 yn minus 2, and so on, then you do not have a general method to solve it. And Leibniz says it's exactly the same kind of problem situation that we have for the differential calculus. Maybe given the time I have, I will not elaborate on that, but we can come back in the question period. So the problem situation seems to be the same. There seems to be an analogy here. Now, how does the story unfold? Initially, people were just writing dd without any abbreviation. This is fairly early in the beginnings of the differential calculus. Leibniz first published it in the 1680s, and it took a while until some people started to understand what he was up to, especially the Bernoulli brothers. So at this stage, it's not in that common of a use. What's for sure is that before 1694, as far as I can tell, and I looked in many places, no one writes that kind of abbreviation. The first significant use of it appears when Bernoulli sends Leibniz a somewhat complicated formula here that will recur in various forms. It's basically something like the Taylor series in an integral form. So you can write the integral of n dz as a kind of infinite series. The details are not super important here, apart from the fact that you have a progression. So from one term to the next, you have increasing differentials, first differential, second differential, third differential, and so on. And Bernoulli does that kind of thing. He publishes about it. He writes dn, ddn, dddn, ddddn if needed. And so, in his reply, Leibniz uses this because he sees that this can be iterated and that maybe you want a general shorthand. And also because he valued that kind of thing, as we'll see later. Why use exponents here for the abbreviation rather than another abbreviatory device? It could be an innocent adaptation of the power case, just like AAA is A3, so DDD is D3, maybe there's nothing to see. Maybe he had his first analogy in the back of his mind, can make some other hypotheses, there are other connections, but there's nothing like what will come out of the story later on. Now, and that's a very interesting thing that happens here. The second step of the story comes when Leibniz extends the proof of Bernoulli's formula. So Bernoulli had sent him this formula here, had published this formula here. The method of proof Leibniz liked very much, and he tried to adapt it, and he tried to get more complicated cases, also because of its connection to the general inverse problems. He was very interested in using this method. And he got general formula. So there's no need to look at all the details here. I just want to highlight some structural features of the formulas Leibniz finds. He wants to express something like this as an infinite series. And what happens, how is this infinite series generated? Basically, nowadays we would call this integration by parts. What happens is that when you move from one term to the next term, you have an exponent in the blue parts that decreases. So you have e, it becomes e minus 1, it becomes e minus 2, you can ignore the constants, e minus 3, and so on. And then in the red parts, you also have the m that changes. Actually, what this amounts to, the decrease here in the exponents of the blue ones is due to the fact that you're actually differentiating something. And here, what's happening in the red part is that you are integrating this, the n part. So why does something strange happen here? If you want to, you can continue this apparently indefinitely. But at some point, since you have an m here, and presumably it's an integer, like 3, you get from 3, I mean, here it's 3, here it's going to be 2, here it's going to be 1. And then you have dn, you integrate it, you'll just find n, and then you'll find the integral of n, and so on. And so progressively, the differentials should turn into integrals. And it seems like you will have to distinguish these different cases given the notation that we have. And here Leibniz thinks, wait a moment. If I write this, if I write d to the power 0 of n is n, and d to the power minus 1 of n is the integral of n, and d to the power minus 2 is integral of integral, and so on, then I can just write the formula as it is here. And I don't need to worry about whether things will turn into something else after a while. The differentials will turn into integrals. This formula would become fully general as written, and you can write it in a fully uniform way. And so he thinks, okay, that's a good reason. Let's do that, and then we have the formula in this way. This, of course, echoes his initial analogy with powers and roots, but I want to point out that actually it does not work at all like Leibniz imagined, because, well, if you have the square root, which corresponds to the square. So you go to the square and then you take the square root. Well, the square is power 2 and the square root is power 1/2. You get fractions. But here, that's not what you have. Here you have negative numbers, which should correspond to the inverses. So it actually doesn't quite align with the analogy that Leibniz had in the back of his mind. But he's saying he thinks it's like a nice unification in this formula here. So he runs with it. And here I want to point out a peculiarity in his methodology. And I think it's clear also from the letters that his correspondents would not have done that and did not do that kind of thing. So Leibniz initially introduced d to the power minus 1 equals the sum as a local trick that allowed him to write a certain formula in a simpler, more uniform way. It's true that he immediately realized that he could generalize it a little bit. So he could also do that on the left-hand side of the formula, but basically not much beyond that. He realizes, oh, it's a bit more general than just this local trick. But still, it's very local. But then he says, he starts writing enthusiastically to other people like L'Hôpital, oh, I have found this. I have discovered that d to the power minus 1 is the sum. This is not a notational convention. This is something I have discovered. And that he unified the calculi of differences and of sums based on this. On this basis, he adopted the notation and explored it further. As it happens, this bet paid off, but it might not have in other cases. Clearly, what I want to highlight is the kinds of decisions he's making here, especially in light of the fact that his claims seem way too strong. And clearly, Bernoulli would not have used this kind of trick. Seems to be a wild overstatement relative to what the notation actually did at this stage. In other words, it seems that Leibniz took the mere fact that this notation permitted writing a certain general result in a simple way as a sign that, so to speak, the notation was right. That, as he put it later, it corresponded to something real. Actually, he will say that once he finds one more thing, and he's like, wow, another thing that stands out when you use this, there's really, it's real. That's how he put it. Okay, so that's one point I wanted to make about the second step. The second point is maybe to worry a little bit about what the notation is doing here. Stop a bit and ponder it a bit. I've been insisting on the pragmatic role of notations. It might seem that more is at stake here. It might seem, at least, especially from a modern point of view, one might be tempted to think that the notation is indispensable to even write a formula such as Leibniz, that you couldn't write it without notation. So of course, there's a sense in which the use of exponents in particular is not essential. You could have written, instead of d to the power 2, you could have written d with a 2 underneath or on top or somewhere else. Could have used indices. But still, if you think about it, you might wonder, is the use of numbers for orders of differentiation with negative numbers corresponding to integrals, is that not indispensable? Does that even make sense to write the Leibniz's formula if you don't have that? Even if, the superficial details look different? And my claim is that's not true. That's actually something that we're projecting on the evidence here. First, I want to emphasize that the d-1 notation is not really needed. The rule for going from one term to the next could be explained in words. Actually, that's what I did at the beginning. You say, well, the m is going to be exhausted. You have to turn it into an integral. And in any case, the formulas like the ones our authors are using are not fully self-standing anyway. Even if you're using the d-1 notation, you still need to understand the rule that underlies passing from one term to the other. You have the etc. and so on. So it's not like the formula is self-standing as it is. And this is not so different. And clearly, for someone like Bernoulli, who's interested in methods, how you write these series, it doesn't matter. You don't need a special notation. You explain, the principle is clear how you generate the terms, right? How you go from one term to the next. You don't need to introduce this kind of device. Right? And actually, this goes even further. Even using exponents, numerical exponents for d, even without the d-1 nifty add-on, is not indispensable at all. You can write any particular instance of the formula without using the notation, and you could convey some kind of generality through examples. And I think it's very clear that this, not only is this possible, but this is what everyone would have been doing at the time. Even 50 years later, when Euler presents that kind of things, he usually presents results by a list of examples, and you see, you can go on. He doesn't try to write these general formulas using that kind of tool. However, there is caveat here, and I think, I mean, maybe I'm contradicting myself a little bit, but I think it's important to see that there's a tension. If we eliminate the notation, Leibniz's results breaks down into a collection of isolated results, united only by the applicability of a common proof technique, basically integration by, I mean, what played the equivalent role as integration by parts in their setup. What would be missing is the idea that they form a single unitary theorem. At least you could argue in some cases it would be there, in some cases it would not be there. And it's, I think the way you write it plays a role in recognizing it as one theorem in a sense. And that's the individuation of results is not independent here from the way you write them. This being said, I'm going to go a bit quickly here because the point I want to make is fairly simple. Then there's the analogy coming into its own. At this stage, the notation is fully established. And I think what happens is that Leibniz notices a certain pattern in his previous formulas. In some cases of them, you actually have one exponent that decreases from term to term and one exponent that increases from term to term. So you have the blue that decreases and the red that increases. And actually, this is the same situation that you had in the binomial theorem, something he would have been attuned to. And that maybe is brought out by the notation. Also, even though it might be there, even if you were repeating these or using different ways, it is brought out by it, and maybe even by the fact that it's exponents. Maybe it's not so important. Nevertheless, I think it's clear that it plays some role. One could argue. Then Leibniz changes notations again to make this even more salient. We can be quick because I want to say a few words about this last step here. Bernoulli's experiments. After that, Bernoulli runs with the notation. It's like, oh, this is interesting. It seems like the differentials behave like exponents. Let's play with this. And he introduced a kind of calculus for manipulating differentials like algebraic quantities using rules like the following. You multiply the second differential with the third differential of y, and then you get the fifth differential. This is not valid at all normally. This is not right. You know, he's playing with it. Should not do that. And here the same, you manipulate algebraically, and he does the weirdest things. So d to the power 0 of y is y, okay, but then d to y over d to y is d0 of y because it's algebraical, so the exponents cancel each other, so it's y. And what about y over y? Well, it's d0 of y. It's 0 of y. It's d0 of y, so it's y. Okay. You need that. And okay, this is a okay. And he has this idea, well, since they are like powers, computing an integral is like getting a third proportional, and he does computations using all of these rules, including this one, you know, you really need it. And he gets correct results actually from a, you know, with hindsight, you could say, well, it only works in very limited cases, but you can, you know, you can clearly see in which cases it will work. From a you know, posterior point of view. And he's even able to derive his Taylor-like formula exactly in this way, using this calculus here. Okay. Does the notation play an essential role here? Are these rules conceivable without Leibniz's notation? Here we have to think again, kind of tricky. You know, strictly speaking, you can write them. But can you write them in general? Can you explain the general principle? Well, so you have d dx times dy over dx times d dy. Well, you know, look, the way this calculus works is you want to cancel the d's that belong to the same variable when you have a fraction. So, you know, you want to cancel this d with this d, so you get d dx. Oh, and here you can cancel it as well, but you have the d, it's only in the denominator, so you have to turn it into a sum. You can explain that kind of thing. You could do this. You could do that. It's not, you get a grab bag of rules. You can try and explain the general principles underlying them.
it's not obvious that you would even think of trying this particular disjunctive combination of strange rules. So it's a very disjunctive thing. In a sense, you could say, well, you could explain it conceptually by treating them algebraically and so on, but it's not clear in this case that it's going to be easy to articulate what the analogy is without seeing it as a kind of way of speaking, as a kind of form of language that allows you to capture it. Could be open for debate. I think what's clear in any case is that it's a matter of accessibility. Even if you could explain all of this, and perhaps you can, it's going to be much more accessible once you have Leibniz's notation and you say, well, they behave a bit like algebraic quantities. So again, an accessibility. Okay, I'm doing good and fine. We can be finished maybe a bit early, even. So let's recap what we saw in this case study. Although Leibniz had an initial idea of an analogy between differences in powers, which may have influenced his initial choice of using exponents, or may not. It is not the analogy he eventually discovered in step 3. The notation itself, by bringing out patterns that would have been less salient otherwise, did play a guiding role here, and also for Bernoulli later on. The new notation reorganized what could be expressed in simple ways, thus transforming what would be a collection of formulas maybe united by a common proof method, or maybe it would just be a proof method, into a single unitary theorem. It allows you to give it that status and maybe file it in your drawer in this way and know in which cases you can use it, and so on. That's what I said in step 2. Also making new symbolic manipulations accessible or more accessible to Bernoulli. This is the thing I just explained. And now the third point I made is that Leibniz's choice and assessment of his notation is guided by his valuing a specific kind of symbolic harmony. So the fact that you can write a general formula where you capture all these cases in a way that has interesting regularities. So harmony is a term that Leibniz sometimes uses. There's a nice study by the historian Eberhard Knobloch on the various ways he deployed this idea, even arguing that perhaps they could be theological background or connection. This, interestingly, I would like to point out a connection here. There has been a literature, especially by Jamie Tappenden, on the question of naturality. So how do you choose, your concepts, which ones are the right ones in mathematics and so on. And he said, well, in the long run, what's natural is what is fruitful. So what guides you in the right direction, in my idiom, if I put it in this way. That's a bit strange if you think about it. If you want to think about practitioners' choices in context of inquiry. So what is a fruitfulness judgment? What does it mean to say, I think it's going to be fruitful in the future? It's not clear. I think in his most elaborate treatment of the issue, 2012 paper in the Journal of Philosophy, Jamie Tappenden goes a bit in this direction. He says, well, if you look at fruitfulness judgments in practice, and there he brings in connections with aesthetics, he says, well, often it will turn into this kind of unity in diversity or whatever that's a bit different from unification, that maybe could be taken perhaps normatively as a sign of productivity of a given line of inquiry. So I don't know how much I buy it, but it's certainly an interesting connection here, and it could be an interesting line of argument. And the two literatures here clearly converge, even though I think the case with notations is much more tractable in the sense that when you talk about concepts, it's a bit fuzzier and hard maybe to get one's hands on, but here it's much clearer. Okay, so one last slide of conclusions. Notations, and more broadly language, matter in mathematics. They orient inquiry and shape the landscape that practitioners explore in multiple ways, impacting not just which symbolic manipulations are easily accessible, but also which conjectures are seen as plausible, and even what can reasonably be considered as a single unitary theorem. So conjectures could be, in a sense, could discuss whether Leibniz's formula is a conjecture or not, how you see its relation to its proof, because it's kind of a generalization as to from a general proof technique. It's not so clear. Bernoulli as well. It's kind of what kind of results I expect and what kind of results I will go towards. So this is what I want to highlight here by saying which conjectures I see as plausible, what can reasonably be considered as a single geometry theorem. But then in return, notations are built and selected in the course of inquiry without the benefits of hindsight as to what the effects of basing inquiry upon them might be. Okay. And that's a subtler methodological matter. And clearly, even here, it involves values, I call them epistemic values, but values nevertheless in essential ways. And it's not so clear even that you want to call it epistemic here. Leibniz has a very different sets of values from Bernoulli or Varignon or so on, and how he thinks mathematics should be expressed, what counts as a theorem and so on, will depend on that. Okay, so that's what I wanted to say from this case study. I hope the general itinerary that I tried to follow is somewhat clear at least. Thank you very much for your attention, and I'm looking forward to it.
All right, we have 2 minutes for more coffee, and then we have plenty of time for Q&A.